Today we're going to look at Turing machines and recursively enumerable languages. So we'll examine languages on which Turing machines halt and on which they don't halt. So let's start with the basic definitions. A language is considered recursively enumerable if it consists of a set of strings which are accepted by some Turing machine. So if there's any Turing machine that accept a set of strings, then that language is called recursively enumerable. Now let's contrast it with what is recursive language. A recursive language is a set of strings that is accepted by some Turing machine, but the most important part is it halts on every single input. Now, let's revise this one more time. Recursively enumerable is a language which will be for any Turing machine. So if there's a Turing machine which accepts a set of strings, in that case, it is recursively enumerable. But it's not recursive if and only if it halts on every input. So what we're saying is that if there's a string which is acceptable by the Turing machine, it's going to halt. If a string that is not accepted by the Turing machine, it will still halt. So only then that language will be considered recursive. So as an example, regular languages are recursive. So on that, in that case, all the regular languages will have some Turing machine that halts on every single input. That's the general idea. So let's look at closure facts. The set of recursively enumerable languages is closed under union and intersection. And the set of recursive languages is closed under union and intersection. So basically both these languages are closed. What does closure mean? It means that for all cases, when union means for all cases. So if there are two languages which are RE, if we take their union or take their intersection, the resultant is also an RE. Likewise, if we take two languages which are recursive and we take their union, then the union is also recursive or the intersection is also recursive. So this is called closure. Now, if we want to talk about a proof for union, so let's suppose there are two languages, L1 and L2, they are RE. What that means is they must have some Turing machines which accept them. So let's suppose for L1, the Turing machine which accepts them is M1. And for L2, there's a Turing machine which accepts them, and that machine is M2. So if we have a Turing machine which simply runs M1 and M2 in parallel, then the resultant is a language which is L1 union L2, because it will accept for both L1 or L2. Any of them which will be accepted, in that case, it will work. So that means the union is something which will halt this big Turing machine, this joint Turing machine, which is a union of the two Turing machines. In other words, this is how we proved it. So RE languages are closed under union. There's a theorem which says a language is recursive if and only if both itself and its complement are RE. So what does that mean? So let's suppose if we have a language which is L, and L is recursive. In other words, the Turing machine for that halts on every possible input. So we have its complement. Complement means that we simply interchange the accept and reject states. So HA is the accept state and HR is the reject state. So in case we both have them, we just simply replace one with the other. Now, let's assume that both L and L complement are RE. That is, they have Turing machines. So if we run the two Turing machines in parallel, at least one will halt and it will give us an answer. So if something doesn't halt for L, it might halt for L complement and vice versa. The next topic to talk about is the printer Turing machine. A printer Turing machine is simply a Turing machine with an additional tape which we call the printer tape. So the printer Turing machine writes strings on the printer tape, and these strings are separated by a symbol, for example delta. Once written, now we don't change this. So this is a Turing machine. So we have the regular Turing machine which just has an additional tape, and we just write strings there, and those strings are not changed. So there's a theorem which says a language is RE, recursively enumerable, if and only if some printer Turing machine outputs precisely these strings. What does that mean? There's two ways. So when you say if and only if, it means a language is RE if some printing Turing machine outputs precisely those strings. And the other way is if there is a printer Turing machine which outputs precisely those strings, then the language for that is recursively enumerable. Let's look at its proof. This is proof by construction. So we'll develop two constructions here. The first one is for printer Turing machine to standard Turing machine. Let's suppose we have a printer Turing machine M. The language is L. Now our goal is to build a standard Turing machine N. So we've got any input X. Turing machine N is going to run M and monitor M. If N ever finds X on the printer tape, so it's going to look for this particular string X on the Turing machine, then N accepts it. So if N accepts the strings in L and does not halt otherwise. So it is going to accept all the strings which are there in L, because when it finds it written on the printer tape, it can halt. So this goes one way. Now for a standard Turing machine to printer Turing machine, let's suppose we have a standard Turing machine N which recognizes a language L. How can we build a printer Turing machine M? The idea is to run N on every possible string in parallel. So it is literally an infinite number of tasks. It simply prints out those that it accepts. So we have the other way around as well. Let's look at now the concept of infinite parallelism. The printer Turing machine works the machine M in rounds. So in round I, so ith round, M will start from scratch. It will generate the first I strings lexicographically. What does that mean? In dictionary order. In that case, and ant, these words, so and will come before ant. this is the lexicographical order, dictionary order. It runs n on each of these strings for I steps. And then any string that is accepted, it simply outputs that. Eventually, every string will be generated, and if we just run n for long enough, and then it will appear in the output. So this is the concept of infinite parallelism. Now we've talked about a lot of things, but there are many languages which are not recursive, and even languages which are not even recursively enumerable. So they don't even have a Turing machine for them. So one thing that you can do for practice is show that the set of recursive languages is closed under reversal. So if we've got a string, we reverse it. So we've got two languages or one language or which we reverse it, and the other language which comes about is also closed. So it's also recursive. So you can practice that proof. So the solution for that is, if L is recursive, then so is LR. R is the reverse of that language. So if L is decided by Turing machine M, then LR can be decided by Turing machine that simply reverses the input and then calls M. It reverses it and then calls M. That's it. That's how we can see that works. So in summary, recursive languages are accepted by Turing machine that always halt. RE languages, on the other hand, are accepted by any Turing machine. If we consider the two languages, they are closed under intersection and union. If a language is recursive, so is its complement. If both a language and its complement are RE, then the language is recursive. And there's a connection with printer Turing machine.